Section 1.5 is going to be analyzing different characteristics of graphs. Okay, so for the, and we are going to use interval notation for the domain and range on these ones. So the first one's saying find the domain and range of each function, and then I am going to express that in interval notation. Okay, if you look at the equation, y equals 1/2 x plus 3, I can tell that's going to be all real numbers because there is no restriction on the x value. If I look at the graph as well, I can see that in the x direction, because domain's x, it goes in the left and right forever, so it is all real numbers. In interval notation, remember that's the one with it that goes from the lowest value comma highest value. It would be negative infinity comma positive infinity, because in the x direction it extends from negative infinity to positive infinity, and then we do use parentheses on this because infinity is kind of an undefined value. Okay, now in the y direction, I can see that this graph goes down forever, and it will go up forever for eventually. So the range is all reals. In interval notation, since it goes down forever, it extends from negative infinity to positive infinity in the y direction, and then because infinity is undefined, we use parentheses on both of those. Okay, for part B, I have a parabola. Okay, if you can use the equation if it's given to kind of figure out the domain and range. I'm going to look at the graph, or actually I might use both. Okay, domain, remember, is the x values. This is a parabola, so I'm thinking from the left to the right is going to express the x values. Okay, so on the furthest left point on the graph, I mean, it is actually extending forever. It's slowly moving to the left, and then if I follow the graph all the way around, it extends to the right forever as well. So in the x direction, eventually this graph will extend all the way from negative infinity to positive infinity, and I do use parentheses because it's infinity. Now in the y direction, it will be limited. It will not be all real numbers. Okay, y direction is up and down, so in the down direction, this does extend forever because there's arrow pointing down. So this will go down forever in the y direction. It does not go up forever in the y direction. The highest y value this graph goes to is right here. Okay, so the highest y value this graph will ever reach is 4. Okay, now in negative infinity is undefined, so I put a parenthesis. Now, does the graph actually touch the 4? It does touch the 4. There's a vertex there. Since there is actually a point at y equals 4, I use a bracket to show that it can equal to 4. Okay, let's look at the third one. Okay, for the third one, it says f of x equals the square root of x squared minus 4. Because they gave me the equation, I could use that to help figure out the domain and range. But I'm going to actually look at the graph. Okay, so domain is the x values. Okay, in the x direction, I'm going to start on the left and go to the right and include all the values from there. So on the left, this actually goes forever. Okay, and then it goes here, and then it kind of stops here. So it starts at negative infinity. It goes all the way to -2, and it does touch -2, otherwise there would be a open circle there. Okay, but then the graph is not done in the x direction. The graph starts up again. So if I keep following the graph, it starts up right here at 2. And then it extends in the positive direction forever. So this starts again at 2, comma, infinity. Okay, so this is representing the domain. It's in 2 pieces because in the x direction, the graph is split into 2 pieces. The u in the middle means union. It means the domain includes the first interval and the second interval. If you're using WebAssign, you can also use a comma, and that will it will accept that as the same thing. Okay, now in the y direction for range, I want to see the lowest y value. Okay, the lowest point on the graph is this one, or potentially this one. They're equally low. They both occur at y equals 0. So 0 is the lowest y value. It does touch it, so it would be a bracket. The only reason it wouldn't be is if there had been an open circle at that point. Okay, and then it extends up forever, ever. Since it extends up forever, it extends to infinity in the y direction. Okay, let's take a look at example 4. It's the absolute value, f of x equals the absolute value of x minus 3. You don't need to use the equation, I could just look at the graph. Let's see, in the domain's the x direction, so in the x direction from left to right, the furthest left this graph goes is forever. Okay, and then it extends right forever. So the domain is negative infinity to infinity. Okay, in the y direction, okay, the lowest y value this graph goes to is right here. It's the vertex. There's no points on the graph that are lower than that point. So the y value there is 0. It does touch that point, so it should have a bracket, and it includes the y value 0. Okay, and then the graph extends up forever, so it's 0 to infinity, including 0. That's the same as saying y is greater or equal to 0. Okay, 2 more domain and range questions. For e, f of x equals the square root of the quantity 9 minus x squared. Since you have the graph, you don't need to use the equation. Sometimes the equation is easier than the graph. Okay, so for the domain, in the x direction, this is the furthest. In the negative direction, the graph goes here, and then it stops here. So it starts at -3, it goes to +3 in the x direction. Okay, and it does include both of those endpoints, so I'm going to go ahead and use brackets. Okay, in the y direction, the lowest y value this touches is here, or on the opposite side, but the y value there is 0. And then the highest y value is right here, that looks like 3, and it does include 3, otherwise it would have some kind of open circle or asymptote or some kind of strangeness going on. Okay, the last one is y equals 1 over x minus 1. That's a rational function. I can tell it's going to have a asymptote at x equals 1. It also has an asymptote at y equals 0. But I am going to express my domain and range in interval notation. Okay, so this goes forever in the left, so that's negative infinity. But there is an asymptote. Where is the asymptote? X equals 1 is an asymptote. So it never actually touches x is 1. So I need to stop the graph at 1. It cannot touch x equals 1, so I'm going to use a parenthesis because it can never equal 1. But it can equal everything lower than 1. It can also equal everything higher than 1. So on the right side of the graph, right side of the asymptote, it goes from 1 to infinity. So it includes all the numbers up to 1, but not 1, and all the numbers from 1 to infinity, but not 1. Okay, now in the y direction, it's similar. This graph extends down infinitely, so negative infinity. Okay, now the y value that's excluded, there's a horizontal asymptote at y equals 0, so the graph will never equal y equals 0. So at 0, I have to stop my range. Don't include 0 because y cannot equal 0. Okay, but it can equal everything above 0 as well. Okay, and it does make sense because my graph is split into 2 pieces, so it's reasonable that my domain and range would also be split into 2 pieces. Okay, now all the graphs above happen to be functions, but if you want to determine if a graph is a function, the most common way to do so is using the vertical line test. If you draw a vertical line through the relation, and it can hit more than one point on the graph at the same time, then it's not a function. And I'm going to show you why in a moment. Okay, so let me look at the first graph. It is a function. I know it's a function because I can tell from the equation. If I were to draw a vertical line here, I can only hit the graph at one point. If I draw it here, I can only hit at one point. There's no place I could draw a vertical line that will intersect the graph more than once. So this is a function. Okay, the next one's not a function. Okay, the reason it's not a function is because if I draw a line through, maybe if I draw it through here, it's going to intersect the graph here and here. Okay, it wouldn't have to be exact graph, but in this case I can read this is -3, 2, and this is -3, -2. Okay, you wouldn't have to list the points, but I'm showing you why this is true. Okay, because it's hitting the graph at 2 places, it is true that the same x value, in this case -3, is being assigned to 2 different y values, and that's why this is not a function. Okay, for the next one, same. If I could draw a vertical line that intersects more than once, it's not a function. I could go here. This is not a function because it's intersecting here and here. I don't need to specify which points because there's actually infinitely many places I could do this, but it's not a function because this is 1, 1 point something, and this is 1, negative some point something. Okay, for the last one, okay, if I try to draw a vertical line, well, I mean, it definitely only hits once here. Even if I get very close to the asymptote, this part is a little slanted, so it's not getting completely vertical. Because of this, these rational functions are always going to be functions. Okay, the next vocabulary I'm going to remind you of are even and odd functions. A function is even if it is symmetric with respect to the y-axis. Okay, a function is odd if it is symmetric with respect to the origin. Remember, the origin was that weird 180-degree rotation. Okay, sometimes it's useful if you see an equation and you know it's going to be even or odd. It'll help you draw the graph or draw other conclusions about that function. Okay, so if I glance at the first graph, I can tell that the left and right side are symmetric across the y-axis. Because it's symmetric with respect to the y-axis, this is actually an even function. Okay, the next one, that's not even, because if I went along the y-axis, the left and right sides are not mirror reflections of each other. But around the origin, if I took this piece and I rotated it 180 degrees, it would rotate back around to this piece over here. So this is odd. Okay, and when I think of functions that are symmetric to the origin, I always think of cubic functions, and that reminds me of a cubic function. Okay, now the last function, okay, if I look at the y-axis, it's not symmetric with respect to the y-axis. It's symmetric with respect to something, but not the y-axis. And there's no way that's rotating around the origin. So this is neither even nor odd, which is what most functions actually are. Okay, example 4, I want you to examine the intervals over which the function is either increasing, decreasing, or constant. Okay, and when they ask you something like that, they want to know what are the intervals of x over which the y value is increasing, decreasing, or constant. Okay, and we do this, we're going to use interval notation, and we're also going to go from left to right. So the easiest way I do this, I just start on the left side of the graph. If I start over here, okay, this graph, is it increasing or decreasing or constant? Well, it's going uphill. It's going uphill, it's going uphill, it's going uphill till here. So the y value is increasing at the beginning because it's going uphill. I'm going to use INC for increasing. Okay, so I started on the left side of the graph. So from negative infinity, it started increasing. It stopped increasing when I got to this point here. What is the x value here? The x value here is -2. So from the x value is negative infinity to -2, the y values were increasing. Now, for increasing and decreasing in constant intervals, I use a parenthesis to not include the -2, because at -2, it's kind of going uphill and it's kind of going downhill, so it cannot be strictly increasing or decreasing at that point. Okay, I'm going to continue analyzing this graph. So from x equals -2, if I follow the graph, now it's going downhill. So the y values are decreasing. They're decreasing until I get to this point right here. Okay, so let's see. I'm going to use DEC for decreasing. Okay, so from x is -2 until x is 2, the graph was going downhill or it was decreasing. Okay, and I am using parentheses here because at -2 and 2, it's not strictly increasing or decreasing. It's a turning point or an inflection point. Okay, now I'm going to keep continuing the graph till I've covered the whole thing. So from x is 2, the graph starts going uphill again, or the y values are increasing. And it does that for the rest of the graph. So it's increasing from x is 2 till forever. So if I go back to the increasing intervals, it started increasing again at 2, and it will continue to increase for the rest of the graph. Okay, let's consider the next graph. Okay, let's see. I start on the left side because it's consistent with interval notation. Okay, if I start on the left side, the graph is going uphill. Up, 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 until I get to here. What is the x value here? The x value there is -3. So this graph is increasing from negative infinity until x equals -3, and these are open intervals because the endpoints cannot be considered increasing, decreasing, or constant. Okay, once I get to x is -3, the graph flattens out. So the y value is remaining constant all along this section here. So that was from x is -3 until x is 5. So it's going to be constant from x is -3 until x is 5. Okay, and then from x is 5, the graph starts decreasing its y values. So it's decreasing from 5 to infinity. Okay, one more graph we're going to consider. Okay, this looks like a cubic graph. Okay, if I start on the left side of the graph, okay, it's increasing. It's increasing, it's increasing, it's increasing. It looks like it's gonna change, but then it's like, nah, I'm gonna keep increasing and increasing and increasing and increasing. Even though it looked like it was gonna level off at 0, 0, it never leveled off for any measurable distance. And if you can't measure the distance it leveled off, then it's not considered leveling off. It's still increasing. So this one actually increases from negative infinity to infinity. It's just increasing at different rates along the way. Okay, the last topic for 1.5 we're going to review is finding the zeros of functions. Oh, zeros doesn't have an E in it. I'm sorry. Okay, another word for finding the zeros is it might say finding the roots. These are also the same values as the x-intercepts. So finding the zeros means find the x values that set the function equal to 0. So I'm going to set this equal to 0. Okay, and then I'm going to solve for x because my roots are always the x's. How you factor is up to you. Some of you group, some of you use the box and the diamond and the square. And whatever you use, as long as you show the correct factors and you know how to do it, I'm fine with that. X equals, what is that, 5 halves and negative 1. So the zeros are 5 halves and negative 1, or the roots are 5 halves and negative 1. If these were actually x-intercepts, I would make it 5 halves, comma 0, and negative 1, comma 0. But this is not actually asking for the x-intercepts. Okay, for b, same. Let's make this, set this equal to 0 and solve it. Okay, if I multiply by x plus 4, that goes away. 3 equals 2x, so I get x is 3 halves. Okay, so the zero or the root of the function is 3 halves. Okay, one more. This is just algebra stuff. Okay, I'm going to go ahead and square to cancel the radical. So 0 equals 15 minus x squared. I might like to move, I'm going to move the x squared to the opposite side so I can get positives. Okay, I'm going to square root both sides. Okay, but remember this is a quadratic since it's x squared, so I should be expecting 2 answers, which in this case are positive and negative square root of 15. Okay, so the roots of this function, or the zeros, are positive and negative square root 15. There are 2 of them. Okay, the last example I'm going to cover is actually from section 1.6. These are graphs of piecewise defined functions. If you know how to graph each individual function, it's just a matter of putting them together and making them work. So for the first function, it says f of x equals x squared plus 1. And this is only true when x is less than or 0. There's several ways to do this. I'm going to graph the whole function and then get rid of the part I don't want. When you get used to these, you'll be able to better decide the best strategy for you. Okay, so if I just want to graph x squared plus y equals x squared plus 1 and I disregard the domain, that would be a parabola that got moved up 1. So it would be something like this, blah, blah, blah. It would look something like this. Okay, but I don't want the entire parabola. I only want the part of the parabola where x is less than 0. Okay, so let me think. If x is less than 0, that's the left side. So I need to actually get rid of all this stuff here. So I only have half a parabola. Okay, and then I also need to consider my domain. So I only graph the parabola for x is less than 0. Now it doesn't say it equals to 0. Since it does not equal to 0, I actually need to put an open circle at 0. And then I extend the graph of the parabola only on the side where x is less than 0. Now I'm going to consider the second half of the graph. So the second half of the graph is the line y equals x minus 2. And I only want to graph that for x is greater or equal to 0. If you can already envision this in your head, then go ahead and just graph the part you need. I'm going to make it too long and then I'll go back and fix it. Okay, so if I'm graphing the line y equals 1x minus 2, my y-intercept is negative 2. My slope is up 1 over 1. Okay, and then I would draw some graph that looks like this. Okay, but hold up. I only want y equals x minus 2 to be used when x is greater or equal to 0. Okay, so I'm going to get rid of, let's see, x is greater or equal to 0 is the right side of the y-axis, so let's get rid of everything over here. I don't want this half of the graph. Okay, now x is greater or equal to 0. It can equal to 0, so I should have a closed circle here. I don't need to emphasize it, but it should be closed. But it does extend forever in the right. Okay, so both of these pieces make up my piecewise defined function. It's called piecewise because it's in 2 pieces. But if you'll notice, this is still a function. It still passes the vertical line test. Even if I drew a vertical line anywhere along the graph, it would pass the vertical line test. If your piecewise defined function fails the vertical line test, then you know you've made a mistake and you need to check the domain on each of your two halves. Okay, let's go ahead and consider one more piecewise defined function because these are a little bit strange and they take some getting used to. Okay, f of x equals negative 2x plus 3 when x is less than 2, and then f of x equals quantity x minus 3 squared minus 2 when x is greater or equal to 2. Okay, it doesn't matter which one you want to do first. I think I'll just work on the line first, and I think I will overdraw it and then I'll erase the parts I don't need later. Okay, this is a line. The y-intercept's 3. The slope is negative 2 over 1. Okay, so it looks something like this. If you have pencil, make it light because you know you're going to erase part of it. Okay, now let me think about this because this is only valid when x is less than or equal to 2. So x is 2 is right here. This is the break-off point in my graph, and x is less than 2 is on this side. So I want to actually get rid of all the rest of my extra graph. So let's see, here's x is 2. Because I only want to include the graph that is less than 2. Okay, so at 2, it cannot equal to 2. So at x is 2, I want to get an open circle, and that point should be labeled clearly. It is at 2, negative 1. If I plugged in x equals 2 in this equation, I would get negative 2 times 2, negative 4 plus 3. So at 2, negative 1, there's an open circle. And then x is less than 2 is going to be on the left side of this line. Okay, now I'm going to consider the second part of this piecewise function. Let's see, x minus 3 squared minus 2, that's a parabola, it's a quadratic. The vertex is shifted right 3 down 2. 1, 2, 3, 1, 2. Okay, here's my vertex. Okay, it would go something like this, but let me consider this before I draw it all in. Okay, I only want to include this graph for the x is greater or equal to 2. So I do want to include the point at 2. X is 2, there's a point right here, which is a little strange, but we'll consider that in a second. Okay, and then greater or equal to 2 would be on the right side. So if I drew this part of the parabola in, it would look like that. Okay, now this is a function, it passes the vertical line test. It looks a little weird because it kind of has it's a part parabola, part line monstrosity. And then you're probably wondering about that weird connection. Okay, this was an open circle here because of the line, but then I colored it in because of the parabola. So there is a point here. It's 2, negative 1. It exists because of the second equation. So this is actually a continuous function. So you don't need to make a distinct circle there. It just needs to continue through there. So if I were to make this more clearly, this is a line, and then it weirdly morphs into this parabola shape here. Okay, and that's my piecewise defined function. They occasionally connect. They don't always connect, but they should always be functions at the end.